Today we're in section 10.5 and we're learning about tangents. So hop on over to your packet and get to your vocabulary section and go to the bottom of the page and you should see tangent. So a tangent is a special type of line. It's going to intersect a circle at exactly one point. So if you look in this picture right here, which you should totally draw in your packet, a tangent line kind of like brushes right past the edge of the circle. So it touches the circle in exactly one point. It's not like crossing through the middle of the circle. It's not like a chord where it connects from end to end. A tangent only touches your circle in one point. It brushes right past the edge of it on the outside. So the point of tangency is that point where your tangent line intersects the circle. So it's exactly one point. It's that one point. In this picture, it's point A, where your tangent line intersects your circle. And then your common tangent is when you have two different circles and they have the same tangent line. So it's a line, a ray, a segment, and it's tangent to two circles at the same time. So we have circle F and circle G, and line L is tangent to both of those circles simultaneously. Or sometimes it might look like this, like they actually share the same point of tangency. So the point of tangency for circle F is the same as the point of tangency for circle G. So this is a good time for you to pause your video and finish filling in your vocab sheet and draw the pictures as well. Okay, hop on over to your theorems page. The first theorem we're going to fill in today is the tangent radius theorem, which basically says that if you have your radius and your tangent line intersecting at the point of tangency, so here's point T, it's the point of tangency, it's where that tangent line L touches our circle. So when your radius and your tangent line intersect at the point of tangency, they're always going to be perpendicular. So your radius and your tangent line intersect and create a right angle. They're always going to be perpendicular. So line L, this line L is tangent to our circle if and only if that line and the radius as T are perpendicular. Remember that little upside down T means perpendicular. They make a right angle. Your tangent line and your radius make a right angle. So if you hop on over to the examples pages for 10.5, we can use this rule to help us find missing values. So if you notice in the first example, HG is a radius, HI is a tangent line. So our radius and our tangent line are intersecting at that point of tangency, They're going to create a right angle. They're going to be perpendicular. So this is a right angle. Oh my gosh, now we have my favorite thing ever, a right triangle. And when we have right triangles, we can use Pythagorean theorem, a squared plus b squared equals c squared. We're looking for the length of GI in this problem, so that's my hypotenuse, that's my C. Or I guess I'll call it X in this problem. And so the first equation that we set up is 9 squared plus 40 squared equals GI squared. I guess I didn't even call it X. Sorry about that. Okay, 9 squared plus 40 squared equals the hypotenuse, GI squared. 9 squared is 81, 40 squared is 1600. I combine them, and then to get from GI squared to just GI, I'm going to take the square root. So the square root of 1681 is 41. So the length of GI is 41. So go ahead, pause the video, finish writing down the work for the first example, and then attempt the second example on your own as you review try problem. So pause the video. Okay, for the second equation, EF is our radius and FG is our tangent line. So here's our right angle. Our radius and our tangent line make a right angle. It's a really janky looking right angle. I'm doing this at home, so I'm not standing at my active board. I'm like doing it all by hand, so that's why it looks a little bit different this time. We can set the Pythagorean theorem 8 squared plus x squared equals 17 squared. And so x is 15. So one thing to sort of keep in mind, this is going to come up later on your homework, is if you look at EG, do you see how right here we kind of cut EG into two pieces? Well, from here to here, that's your radius. Whenever you go from the center of your circle to the edge of your circle, that's the radius. So this right here is 8. Because the radius from E to F was 8. So from E to the edge of the circle right here is also going to be 8. So maybe the problem might ask you, instead of trying to find X over here, maybe X is this little nugget that we don't know, like this outside part, this line right here. So if we can find that whole side, EG, and then subtract the radius, that might be a strategy we would need. So like this one would be 9. 17 minus 8 is 9. So just kind of keep that in mind. That might come up later in your homework or something. I don't know. Okay, hop back over to your tangent sheet. Or sorry, not tangent. That's what we're talking about. Our theorem sheet. And the next theorem is the congruent tangents theorem. So the congruent tangents theorem says if we have two segments, two different tangents that intersect at a common point. So these two segments are tangent to the same circle and they intersect at point B. That means that they're going to have to be congruent. So in this example, AB is tangent to circle D. CB is tangent to circle B. They meet at point B, and so that means that they're congruent. AB and CB are congruent. They have to be congruent to each other. So go ahead and pause your video, finish copying that down. On our example, hop on over to the examples page. I see that PW and QW are tangent to the same circle, both tangent to circle R. They intersect at point W. And so that means that we can set them equal to each other. PW should be equal to QW. They're congruent. I can set them equal, and I can set up an equation. 3x minus 6 equals x plus 10. Set them equal to each other. They have to be the same. I subtract x. I add 6. So I get 2x equals 16. Then I divide by 2. And x is 8. So go ahead and pause your video. Ooh, what's happening? Pause your video. Finish copying the theorem. Finish copying on the example. And then when you're done, attempt this problem as your U-try problem. So go ahead and pause the video. Okay. We have two tangents to the same circle. They intersect at point A. So AB and AC are congruent. I can set them equal to each other. 4x plus 2 equals 2x plus 8. Then I subtract 2x and subtract 2 to get 2x equals 6. Divide by 2 and you get x is 3. So your final answer is x is 3. And if you wanted to check it, you could take the 3 and then go plug it back in. 4 times 3 is 12. 12 plus 2 is 18. But whoa, 12 plus 2 is 14. Whoa. 12 plus 2 is 14. So AB is 14. 2 times 3 is 6. 6 plus 8 is 14. So you get both of them to be 14 when you go plug that 3 back in. That's a good way to check and make sure you did the problem right. And then last but not least, this is an application of that rule that we just learned about congruent tangents. So we have a triangle, but really this triangle is just created by a lot of different congruent tangents. So if you notice right here, TQ and QU are both tangents. They meet at point Q, so that means that they are congruent to each other. So QT and QU are both going to be 4. So QU is 4. Okay, then SR is 13, and SR and UR are both tangents that meet at the same point. They both meet at point R. So they're going to be congruent. So this is 13 as well. So they're tangent to the same circle and they meet at point R. So they're congruent. And then the last two tangents, PT, the struggle, and PS are congruent. So if PT is 9, then PS is 9. And so if I want to solve for x, I can set up 2x equals 9. And then you divide by 2, and x is 4.5. So let's find x. And then the perimeter, you're going to add up all of the sides. So for PQ, we have 9 plus 4, which is 13. So side PQ is 13. Side QR is 4 plus 13, which is 17. And then the third side of the triangle is PR, which is 9 plus 13, which is 22. And so then our grand finale for our perimeter is 13 plus 17 plus 22, which is 52. So there we go. X is 45 or 4.5. 4.5 and perimeter is 52.